Our topic for today will be other thermodynamic functions and to ultimately derive the Maxwell relations. Not to be confused with Maxwell's equations, same person, completely different discipline. Heat, work, energy, entropy are extremely important physical quantities in thermal physics and statistical mechanics. But in this lecture, we're going to focus on some other potentials that are also of interest. And so, to name a few, we're going to be talking about enthalpy, we're going to be talking about Helmholtz free energy, and we're going to be talking about Gibbs free energy. These three functions are known as thermodynamic functions. Let's start with something we already know and then move on from there. We'll start with energy and entropy. I can write the first law of thermodynamics in the following way. This is just what we call the thermodynamic equation. And let's talk about the quantity of interest will be energy and entropy for this first section. We're going to treat entropy and volume as independent variables. And so if I'm going to take a differential of energy, I might write it in the following way. I can write it as dE ds at constant v plus dE dV at constant s. Now from this equation, we can see immediately, if I'm looking at the relationship between these two equations, I can see immediately that I can write T as du dE ds at constant V, and pressure as minus dE dV at constant S. Now, in order to guarantee that du is an exact differential, which it has to be, it must be that the mixed partials have to equal one another. So what that means in this case is when I take second derivative of the energy with respect to the volume and then the entropy, it has to be exactly the same as the second derivative of the energy with respect to the entropy and the volume. Which is to say, if I take dV at constant S, du dE ds at constant V, that has to be equal to d ds at constant V, dE dV at constant S. That being the case, that means that if I take the second derivative, if I take the derivative of both sides with respect to volume, it has to be that dt dV at constant S has to be equal to minus dP ds at constant V. And this is what we call the first Maxwell relation. It relates functions of volume and entropy. And this is one of what we call the four Maxwell relations. It's going to be second verse same as the first for the next three permutations. And we will get 3 more Maxwell relations that look similar to this one. So let's talk about enthalpy. Enthalpy is defined as the energy plus pressure times volume. If we begin with PdV, by the chain rule we can write this as the derivative of PV minus V dP. So if we return to the first law expression again, we get du is equal to T ds minus P dV, which is T ds minus D dV minus V dP. If I combine terms, I can get D of U plus PV, which is of course dH, is equal to TES plus V dP. So my independent quantities in this case are going to be entropy and pressure. Not entropy and volume, but entropy and pressure this time. And I move along the same trajectory I did before. I can say dH ds at constant T is equal to T, dH dP at constant S is equal to V. When I take the mixed partials of those two functions, they have to be equal, which tells me that dt dP at constant S has to be equal to minus dV ds at constant P. Oh, sorry, plus at constant P. This is my second Maxwell relation. What does this mean? The physical meaning of enthalpy is that the sum of the internal energy plus a PV term that's often associated with the work required to make space in an environment to actually house the system of interest. So this is essentially the work that has to be done to push the atmosphere out of the way, according to Schroeder, and to make room for the system that we want to operate on. Enthalpy changes are caused by heat and forms of work that are not compression and not expansion type work. By the same token, if you destroyed the system, the enthalpy is the energy that you could recover in the process. That is to say, it would describe the energy of the system and the work done by the collapsing atmosphere. Another way to talk about enthalpy is to say that if you increase the temperature of a system at constant pressure, the heat capacity at constant pressure is the same as the change in the enthalpy. In other words, while we used to talk about the heat capacity at constant volume as being the change in energy with respect to temperature at constant volume, the heat capacity at constant pressure can be written as the derivative of the enthalpy with respect to temperature at constant pressure. That's another nice relationship. Enthalpy has a lot of applications in chemistry and engineering. Power and refrigeration are two of the areas where engineers utilize tables to calculate the enthalpy. Physicists don't tend to do that. You'll see in chemistry texts and engineering texts these tables in the back, numerous tables that have enthalpies and such. You can do things like saturation or ionization phase changes and so on and so forth. But that's one of the thermodynamic potentials that we'll talk about it occasionally, not all that much, in statistical mechanics. Another quantity that is really pervasive, much more pervasive, I think, than enthalpy in physics is the Helmholtz free energy. Certainly in statistical mechanics, We use the Helmholtz free energy quite a lot. Let's maybe think of it in these terms. Suppose you have a constant temperature environment. In this case, a system can extract heat or thermal energy from the environment at no cost. All we have to do is create a system from nothing, and the only work entailed is just creating that system for that purpose. On the other hand, if you destroyed that system, you would get that energy back. Or whatever energy, you wouldn't get all of it back. The second law of thermodynamics says you can't break even. We'll talk about that further as well. But whatever energy you get back would be what we call free energy. And we have an expression for the Helmholtz free energy, which I keep using U and really mean E, energy minus the product of the temperature and the entropy. So the Helmholtz free energy is the total energy needed to create a system minus the heat that you get for free from an environment at constant temperature. So, F is the energy that must be provided as work if we want to create the system out of nothing. It's not really free when you're creating it. If you destroy the system, though, you get the energy back for free. I think that's where the term comes from. It's kind of nebulous and certainly confusing. Nonetheless, we write out our first law equation again. I'm going to write this as d Ts minus s dt minus v. And so df looks like df dt at constant v plus df dv at constant. So my variables of interest in this case are dv. If I compare this to my thermodynamic potential equation, or my thermodynamic equation, I get that S is equal to minus df dt at constant V. P is equal to minus df dv at constant T. Once again, the drill is that the mixed partials of those functions have to be equal because these are exact differentials. If that's the case, if I take the derivative of the first term with respect to v, holding t constant, take the derivative of the second term with respect to t, holding v constant, I'm going to get that ds dv at constant t is equal to dp dt at constant v. So that is the Maxwell relation that I am able to derive from using the Helmholtz free energy. Well, the last thermodynamic potential in this vein is the Gibbs free energy. Now consider a case where we have an environment of constant temperature and pressure. The work that I need to create or destroy a system is called the Gibbs free energy, and we define it by E minus Ts minus PV. It encompasses the system's energy less the heat term from the Helmholtz free energy, and in addition to the atmospheric work term that came from the enthalpy. So it takes them both together. So for the case of Gibbs free energy, our independent variables are going to be T and P. And so once again, the last time we do this drill, TDS minus PdV, and I can set that equal to D TS minus S dt minus d PV plus V dP. By the definition of the Gibbs free energy, dg then is equal to dg dt at constant p plus dg dp at constant t. If I look at how these two equate, I'm going to find then that I end up with S is equal to minus dg dt at constant pressure, V is equal to dg dp at constant temperature. Again, equating the second partials gives me minus ds dp at constant t is equal to dv dt at constant t. And this is my fourth Maxwell relation. This one relates to the Gibbs free energy, another term that we'll use quite a lot in studying phase equilibria and will become important to us in other areas as well in statistical mechanics. And we will use these functions as we move on. What I'd like to do at this point is we have completed our work in investigating these sort of alternative thermodynamic potentials. The next step that we're going to take in the next lecture is to study phase equilibria. Thank you.